Hello friends, welcome to the lecture series of oscillation. Today I shall show you some Lissajous figures and how it can be generated. So this is basically can be generated by superposition of simple harmonic motions. Okay, so let's see. So now let's see how the superposition principle is. If a particle is acted upon by two separate restoring force, each of which can produce a simple harmonic motion, and the resultant motion of the particle is a combination of two simple harmonic motion. So if we consider one such oscillation equation is x1 equal to a1 sin omega t, and another one is x2 equal to a2 sin omega t plus phi. So the resultant amplitude we can write x equal to x1 plus x2 and we get this form. So you can see this capital A is the total amplitude of the resultant oscillation, and it depends upon the phase that extra phase basically that x2 has, that is the phi angle. Okay, now in the next slide we will see, depending upon the phi, how the resultant amplitude will be varying. You will see graphically, okay, in picture. Okay, now you can see if cos phi equal to 1, that is the x1 and x2 oscillation are in same phase, then you can see the resultant amplitude, that is a1 plus a2. And if they are in opposite phase, it becomes a1 minus a2. So the resultant amplitude will reduce, right? So in the next slide we will see that if we have two waves, they are basically in perpendicular direction, x and y, so what will be that form? Now you can see the two forms of the simple harmonic motions which are in perpendicular direction. So if we put the form of x in the expansion of y, you can see that sin omega t plus phi we can expand is sin a plus b. So there, if we use the form of x equal to a1 sin omega t, the form which we are getting, it is nothing but equation of a ellipse, where in the x-axis the amplitude is 2a1 and in y-axis the amplitude is 2a2. Now if we change the angle phi, that is the phase difference between the two waves phi, how this form will change? So it is the general form, it is the equation of the ellipse. Now if we change it, how it will be varying? Let's see. So now if we put a phi equal to 0 in the above equation, we are getting the equation of a straight line, that is y equal to mx. Here m is a2 by a1, right? So now you vary the phi and let's see what we are getting. So if for phi equal to pi by 2, we are getting x by a1 square plus y by a2 square equal to 1. That is the equation of a ellipse. So for phi equal to pi by 2, we are getting equation of a ellipse, and the figure is looking like the ellipse. It is the Lissajous figure for this case. Okay, now let's see if a1 equal to a2, the amplitudes are same, the equation becomes x square plus y square equal to a square, right, for phi equal to pi by 2. So you can see, depending upon the initial phase difference, how this form is changing. Okay, now we will see that if phi equal to pi, then they will be in out of phase. So initially we saw phi equal to 0, now it is phi equal to pi. So you can see the angle, basically the slope is negative. Now if the frequency are not same, here in this case you can see x equal to a1 sin omega t and y equal to a2 sin 2 omega t. So you can see how it is varying, and if it is 1:3, then how it is varying. So initially we have seen there are 2 loops, now there are 3 loops. So basically the number of loops depends on the frequency ratio 1 is to n. So if we change the frequency, if the frequency ratio is like that, means finding out the number of loops, we can tell what is the frequency difference between two waves. Okay, thank you.